All right, in this video, we'll try to make what we've seen in the last example more precise. We looked at two matrices that were similar. We actually got the P from the question, and then we found that the characteristic polynomials were the same, but that the eigenspace were not quite the same. I mean, they were similar, there was some relationship, but it wasn't clear. And so let's try to make this precise. So proposition 3.3.2 will do that. Assume that A and B are similar matrices. Let's say that B is P inverse AP. Then A and B have the same characteristic polynomial. So what we saw in the example was not random. They will always have the same characteristic polynomial. That gives us a bunch of things. It gives us that A and B have the same determinant and trace. It will give us that A is invertible if and only B is invertible. It will give us that lambda is an eigenvalue for A if and only if lambda is an eigenvalue for B. And so that's why in the last example, we looked at 2 and 4 for both. The eigenvectors will not be the same though. It says that V is an eigenvector for A if and only if it's P inverse of V that will be an eigenvector for B. Okay. And for any eigenvalue lambda of A, the dimension of E lambda A is equal to the dimension of E lambda B. So they will not be the same. They have this relationship here. Part of the reason we got the same basis in this case is the fact that our matrix P and our matrix P inverse have a nice 1, 0 here. So part of the space is not moved when you multiply by P. So they have one basis element in common in some sense. All right, so let's prove this. I want to consider PB of X. So that's the determinant of, sorry, B, not A, of B minus Xi. I know that B is P inverse AP minus X, and I'm going to write I as P inverse. I'll even put I just to make it as clear as possible, right? This is a really silly way of writing I, but now I can factor P inverse from both sides. So that would be the determinant of P inverse, determinant, oh, sorry, let me factor it first. I'll split it afterwards. Then I'm left with A minus X I P. The X can go anywhere, so we'll put it with the I. And now if I split it, I get the determinant of P inverse, determinant of A minus IX, determinant of P. Now these are all real numbers, and so I can bring determinant of A minus IX up front. And then, actually, let me write it this way first. And then I could put the inverse outside, determinant of P. And so I get that these two cancel, and I'm left with only determinant of A minus IX. All right, I'm left with only PA of X. Nice. All right, so the characteristic or the polynomials are the same. Now, PA of X, that's, if you remember, that's minus 1 x to the n plus minus 1, sorry, to the n minus 1 trace of A x to the n minus 1, then a bunch of terms. Final term is determinant of A. And P of B is the same, but with B's, sorry, trace of B, xn minus 1 plus determinant of B. And so if these two are the same, that means their coefficients are the same. And so determinant of A, which is the constant term, is determinant of B. Trace of A, which is the part of the coefficient of x minus 1, is equal to the trace of B. All right, that's 2. I want to show that A is invertible if and only B is invertible. Well, A is invertible if on and only if determinant of A is not 0, but we just said determinant of A is the same as determinant of B, and so determinant of B is not 0, same number, and so B is invertible. All right, now I need to show that the eigenvalues of A are the same as the eigenvalue of B. Well, the eigenvalues of A are the zeros of the characteristic polynomial PA of x, which is PAB of x, and so um, they are exactly the eigenvalues of B. Excellent. these are these are quite fast, eh? All right, so let's prove this one. This is a bit more complicated. Not much. If V is an eigenvector for A, I want to show that P inverse of V is an eigenvector for B. So let's consider W, which is P inverse of V. I want to prove that it's an eigenvector for B. So I'm going to, let's put arrows here. I want to multiply W by B. So that's the same as multiplying W by, B was P inverse AP, and then W is P inverse V. Hopefully you can see here that P and P inverse cancel. And now V is an eigenvalue for A, so I'm going to get P inverse of lambda V. And the lambda is just a real number, so it can move. I can place it up in front, and so I get lambda P inverse of V. P inverse of V is W, so I get lambda W. And so yes, W is an eigenvector. It has the same eigenvalue as of B. Actually, let me move this. It's so much in the way. Is an eigenvector of B with eigenvalue lambda. All right, so in fact, what we get, and that's going to give us 6. I mean, the eigenspaces are not the same. We saw that in this example. They're not identical. Sorry. They're not identical. These and this is not the same. But we now know how to match them. So we have an isomorphism from E lambda A to E lambda B, which sends V to P inverse of V. In fact, so we know that, and we have a name for this, that's the linear transformation associated to P inverse. So multiplying everything by P inverse matches these two. And so the dimension of E lambda of A has to be equal because they're isomorphic vector spaces.